One of the things the book covers that I feel like maybe doesn't deserve as much attention as the book gives it is the idea of impulse. This is integral of force over time, which of course could be very simple if the force is constant. It could be a complicated integral otherwise. The reason I don't feel like it needs so much attention is it's really just the change in momentum. If we do integral of f dt, we get dp dt. We integrate that, we get delta p, just the change in momentum. It doesn't really need a different name. This is commonly used when you start talking about the collision of, say, a ball with a bat or a golf club, something like that. You look at the force profile as a function of time, and that can be a complicated mess. And when you do the integral, you get the change of momentum, which is one thing to keep in mind, we're always going to consider conservation of momentum to be valid in pretty much any problem we do, because as we mentioned, if you keep the window before and after the exchange of momentum small enough, you can consider it to be no change in momentum. Kinetic energy, however, is not conserved. In a real collision between macroscopic objects, and that means things big enough to see, kinetic energy won't be conserved because there will be sound or heat, or the objects will be deformed, and all those things. There are sometimes sometimes it's not a bad approximation to have things like steel spheres colliding at low speed, so there's not a lot of damage or deformation and not much in the way of sound or heat. We can use this to classify collisions as one of three types: elastic, which is this rare kinetic energy before and after are equal; inelastic, which is everything else where it's not; and completely inelastic, where not only are kinetic energy before and after not equal, but the two things stick together and become one, like if you threw two wads of gum at each other. As an example of this, we can look at the ballistic pendulum. The purpose of this was to find the velocity of a bullet before the invention of lasers and stopwatches and photogates. And what we do is just take a large block of wood, we get its mass, and we hang it from a couple of strings. We have the mass of the bullet, and we make the block big enough for the bullet to get all the way through. So the bullet hits the block when you fire it out of the gun, it burrows in, and then stops, and the bullet and block will swing back and up a little bit. As they do this, since this will be very slow, typically 1 or 2 meters per second, we can measure this change in height relatively easily, and we can use conservation of energy to say that the potential energy of the bullet block system at this height is equal to the kinetic energy it had right after the collision. We put these two things together, we get that the velocity after the collision is square root of 2gh. We can then use conservation of momentum to look at the collision and see how the bullet and block ended up with this velocity vf. Initially, all the momentum was carried by the bullet. We have its mass times its initial velocity. After the collision, it was all carried by the block and bullet. So we can solve this for bullet's initial velocity in terms of final velocity of block and bullet. We have an expression for that, so we can write this. The most common mistake students make when they're doing this problem is they want to conserve kinetic energy. They want to say the kinetic energy the bullet had in the first place is equal to the kinetic energy that the block and bullet have at the end, and this is just wrong. Energy is, of course, conserved, but there are a lot of different kinds of energy in this problem. It takes some amount of energy to push a bullet through a block of wood and tear all those fibers and everything associated with it. It's a large force over some displacement. We have no idea what that force is. We have no idea how much the bullet is heated up, how much it's deformed, the sound it makes. If we had formulas for all those energies, we could solve this with conservation of energy when we added all those others over here to the right. Since we don't have any way to know that, we have to use conservation of momentum. If we put in some reasonably realistic numbers, 20 grams for the bullet, 5 kilograms for the block, and a height change of 12 centimeters, we get 385 meters per second. Now, just to check, what's the initial kinetic energy of the bullet in this case? 1/2 mv bullet squared is 741 joules. What's the kinetic energy of the block plus bullet? Notice if you'd done this the wrong way that I mentioned above, you get 741 for that again. But when you do it the right way with conservation of momentum, you get 5.9 joules. This is less than 1% of the initial kinetic energy. So all the rest of it damages the bullet and the block and makes noise. If kinetic energy was really conserved, if you were wearing a bulletproof vest, you'd pretty much be okay. Nothing could happen to you rather than a seriously damaging punch. If we make this assumption that kinetic energy is conserved, we take a 5 kilogram block and replace that 5 kilogram block with a 100 kilogram person and keep the bullet mass and velocity, we would get this, that your velocity changes by 5 meters per second. Bullets would not be particularly dangerous if all they did to you was give you a small speed bump of 5 meters per second. It might make you trip, but it's not going to kill you. The most general problem we could try and solve here would be a 3D collision. The physics is not much harder than in the 1D case because we're just going to do 3 1D problems. The real problem is trying to describe angles in 3D. And if you're interested, you can go to Wikipedia or Google and look for Euler angles. We're going to do 2D problems because there's nothing really new to be added in 3D. We simplify the 2D problem by first assuming we have a moving object and a stationary object. The moving object is a projectile, stationary is the target. This isn't really as big a restriction as it may sound like because if they were both moving, you could just imagine that you're riding along on the second object or you're running along beside it. You would then see it as sitting still and the first object would be faster. To be smart, we also pick the direction of motion along the x-axis to be direction of the incoming projectile. This is just to make the math easier when we get here further below. So let's say we have a 2.5 kilogram projectile moving at 20 meters per second and it hits a 1 kilogram target. And what will probably happen is they'll both go away at some angle to the initial direction. So we look at what we know and what we don't know. We don't know the final velocity of the projectile, final velocity of the target, either of the scattering angles. So that's 4 unknowns. How many equations do we have? Well, in 2D, our vector equation for conservation of momentum gives us 2 equations. If we only have 2 equations, we can only find 2 of the 4 unknowns. If we're told kinetic energy is conserved, and this is a giant if, that would give you a 3rd equation. You'd still need to be given one of these things, one of these 4, or nobody could solve it. If you can't make that assumption, if you weren't told that this is an elastic collision, then you have to be given 2 of the unknowns. So let's say we have the 2 unknowns, v1 final is 17 meters per second and theta 1 is 10 degrees. Using conservation of momentum, px initial is m1 times v1x initial, which is our 20 meters per second since we picked our x-axis to lie in this direction. Now, if we then calculate that, afterwards we get m1 times v1 final x plus m2 times v2 final x. We know the initial stuff. The final stuff, we've been given that as well. What we don't know is v2f and cosine theta 2. But we can reduce this down to something. We can find out what v2 cosine theta 2 equals. And it's 8.15 meters per second. In the y direction, we do the same thing, and this is why we picked the axes that we did. Now the incoming y momentum is 0, because we picked the x-axis to be in the direction of the incoming particle. Final y momentum, these 2 things must cancel, the piece from the projectile, the piece from the target. Again, we know all the projectile things. We don't know the target things. We can do some algebra and reduce this down to v2f sine theta 2 is negative 7.3 meters per second. We can divide this equation that we just got by the first one. The v2f's cancel, and we get that the tangent of theta 2 is negative 0.906. Theta 2 is therefore negative 42.2 degrees. And notice it has to be negative because theta 1 is positive, and we can't measure positive in 2 opposite directions. We then plug this into either of these equations, the top one or the bottom one, and we can solve for V2F, which is 11 meters per second. Now we can see, was kinetic energy conserved? Here's our initial kinetic energy, our 2.5 kilogram projectile moving at 20 meters per second, 500 joules. At the end, our 2.5 kilogram projectile is moving at 17 meters per second, and our 1 kilogram target at 11 meters per second. We put those together and we get 422 joules. So we lost about 78 joules. That's about 15% of the incoming kinetic energy that went into deforming the spheres or making sound, light, heat, whatever.